Good morning, students. Today we are going to know about what exactly the stack memory and how that particular stack memory is going to be accessed by the 8086 microprocessor. Not only the 8086, any kind of microprocessor, but accessing the stack memory in case of the microcontroller is going to be different approach, but in case of the microprocessor or any kind of microprocessor, it is going to be the same process. Okay. So how exactly the stack is going to be accessed by the microprocessor and how exactly the stack is playing a major role when you are trying to run a program or the application. Means if you are trying to run a C program, when you would like to execute one C program, how exactly the stack is going to be utilized by the microprocessor. And when you are trying to open one application, for example, if you are opening your WhatsApp to WhatsApp application or the Facebook application, when you are trying to open one application, obviously the stack area is going to be used by the system. The stack area is going to be used by the system. So as we know that the stack is nothing but a part of the RAM memory is used as a stack. A part of the RAM memory is used as a stack, which is used by the microprocessor during the execution of the program to hold addresses as well as the data during the execution of the program temporarily. So the main intention of the stack is 8086 microprocessor or any kind of microprocessor is using a part of the RAM memory as a stack to hold addresses as well as the data temporarily during the execution of the program. During the execution of the program. Now you may ask me one question, sir. We know about the addresses, data. Then what is the use of the address? Okay, so we'll see all those things one by one. But before that, what I would like to do means I would like to define some parameters which we have not defined initially. So after defining that one, we'll come to the stack area, because if you realize that one, then the stack is going to be very easy for you people. Okay, so I'll take the window. Okay, I'll take my window. This is the stack. So let us define few parameters. What exactly the bit? So we are supposed to know about a particular one called as a bit, and another one is called as a nibble, another one is called as a byte, another one is called as a word, another one is called as a table. Okay. So what exactly the bit? What exactly the nibble? What exactly the byte? What exactly the word? What exactly the table? What exactly the table? Okay. So bit is nothing but a binary 0 or 1. Bit is nothing but one bit position. That bit may be the binary 0 or binary 1. So here what I am doing is I just took the 16-bit combination. Sima, from here onwards, remember that when you would like to represent the data bit positions are going to be. When you would like to represent the data, that may be the 1-bit data or the 4-bit data or the 8-bit data or the 16-bit data or the 32-bit data, whatever the data it is. When you would like to represent the data positions are going to be indicated using the what data points. Just like means when you are going through the textbook, you will come across the these bit positions. Means what exactly the use of this particular one means these suffixes are indicating the data bit positions. These suffixes are indicating the data bit positions. So even though we have the what is that data bit positions, 16 data bit positions from 0 to 15. 0 to 15 is see, and another case is if you are not aware. I am assuming that you people are not aware of the bit positions. So based on that, I am giving the explanation, because some of you would have not remembered the concept of how exactly the bits are going to be represented. So that's why I'm considering this particular concept. Don't bother about it. So here, when you would like to assign the data bit position to the binary bit combinations, you should move from right to left. You should move from right to left concept. You should move from right to left. Okay. So means let me take this one in another way. You should move from right to left concept. Means I'm going to assign the first bit position to this one, and next bit position, and so on. So for my bit explanation, even though I'm having the 16-bit combination, which is varying from 0 to 15, 0 to 15 totally it is going to be the 16. Okay. Now. So in order to indicate a bit combination, I'm just taking only the D0 bit. I just highlighted that it is the bit position. So this bit may be, it may be the 0 or it may be the 1. Okay, now the bit combination, when you are going to write any binary combination to a particular bit number, it is going to be vary from minimum to maximum. What exactly the minimum to maximum, I'll let you know, no problem. So bit is nothing but it may be 0 or 1. Bit is nothing but it may be 0 or 1. I just took the D0 to indicate that the bit position is a D0 and whose value may be the 0 or 1. Whose value may be the 0 or 1. The next case is, I would like to, again I am saying that when you are, what is the use of these bit positions, why we are using the D suffixes means they are indicating that they are the data bit positions. They are the data bit position to indicate the bit position of a particular bit combination as a data. We are taking the D suffixes D0, D1, D2 and so on to D15. Make an habit of remembering this concept because throughout the microprocessor concept we are going to use this kind of explanation only. Okay. So if at all you would like to represent the 16-bit combination of address lines. Okay, the 16-bit combination of address lines. Here we are taking the data, and if you would like to represent the address lines, then the D suffixes are going to be replaced with the A suffixes like A0, A1, A2, and so on to A15. If it is a 16-bit combination. If it is a 20-bit combination, as we know that 8086 is supporting the 20-bit address bus, then it is going to be vary from A0 to A19. A0 to A19. Okay. So means if the bit combination is the address, then they are indicated with the A suffixes. If the bit combination is the data, they are indicated with the data D suffixes. Okay, just remember that. So bit is nothing but it is a binary 0 or binary 1. Bit is nothing but binary 0 or binary 1. The next one is called as a nibble. Okay, nibble is nothing but, see here we are interested to explain the nibble. So I am not typing anything. So you please note down if you are not aware of this particular nibble. Nibble is nothing but group of 4 bits is called as a nibble. Group of 4 bits is called as a nibble. Previously, group of 1 bit. Only 1 bit is called as a bit. That bit may be the 0 or 1. So here the nibble is nothing but group of 4 bits. So here I took the 16-bit data bus now. So 16-bit data lines. So out of 16, I just highlighted the 4. I just highlighted the what is that? The 4. So D0 to D3. I just highlighted that D0 to D3. They are the 4-bit combination. Nibble is nothing but group of 4 bits is called as a nibble. Group of 4 bits is called as a nibble. So as we know that the first combination of the nibble is going to be the 000 and the last combination is going to be, I think you are not seeing this one. So that's why I'm ending this presentation. Now I'll go the window presentation because my video is going to be opposite display. Okay. So here what we are having, this one first combination. It is a 4-bit nibble is nothing but 4-bit number. So the first combination of the nibble is going to be, first combination of the nibble is going to be the 4 zeros. Okay. Now the last combination of the nibble is going to be the 4 ones. So from here onwards, I am going to say, or I am going to use one word called as a minimum to maximum bit combination. Minimum to maximum bit combination. Minimum bit combination is nothing but what? It is going to be the 0 0. Minimum bit combination is going to be the 0 0. Maximum bit combination means all the bits are having the ones. Maximum bit combination means all the bits are having the ones. All the bits are having the ones. All the bits are having the ones. So minimum combination, the 4-bit binary data is varying from 4 zeros to 4 ones. So I'm having we are having all the bit combinations. We are having all the bit combinations like triple 4 zeros, 0001, 0010, 0011, 0100, all those things. Okay now. So here the 4-bit combination is nothing but in the number system we are going to take it as a hexadecimal number system. We are going to take it as a hexadecimal number system. Besides this particular 4-bit combination, what I done is I took the hexadecimal number representation also. Okay, so means if it is a 4 zeros, then the hexadecimal bit position is going to be 0. If it is a 0001, it is going to be the 1. Next one is a 2. Next one is a 3. Means in order to represent the 0, 1, 2, 3 or otherwise our hexadecimal numbers, they are varying from 0 to f. In order to represent that that particular hexadecimal number, we are taking the 4-bit combination. We are taking the 4-bit combination. For from here onwards, remember that we are when I am taking a bit combination, that may be the 4-bit combination or the 8-bit combination or 1 bit. 1 bit means only we are having the 2 bits 0 and 1. So if it is the 4-bit or the 8-bit, all those things, then I am going to use one word called as a varying the bit combination from minimum to maximum. Varying the bit combination from minimum to maximum. Here the minimum is a 4 zeros, maximum is a 4 ones. Minimum is a 4 zeros, maximum is a 4 ones. Okay. Now. So here how many combinations we got using the 4 bit? To calculate that one, 2 power 4 we are going to apply. Okay. Now we are having the formula address how many address combinations we are getting using the address bus na same concept. Here we are taking the base of the binary number system to the power of number of bits. Base of the binary number system to the power of number of bits. How many bits are there in the nibble? We are having the total 4 bits are there in the nibble. So in order to know how many combinations we are going to get using the 4-bit number, we are supposed to take the 2 power 4. We are supposed to take the 2 power 4. Okay now. So if it is a 6-bit 5-bit combination, I am going to take the 2 power 5. If it is a 6-bit combination, I am going to take the 2 power 6. 2 power 4 is nothing but 16. So we are having the 16-bit combination. Okay now. So just remember that nibble is nothing but group of 4 bits is called as a nibble. Group of 4 bits is called as a nibble. Next case is so here in order to explain my thing, I just take the 4-bit combination as a separate color code. So it means I just highlighted with a red mark. So here these 16 bits are equal, means 4-bit combination where you are varying from the minimum to maximum. Remember, minimum to maximum means we are considering all the combinations. They are varying from the minimum to maximum. So if you are taking the minimum to maximum for a 4-bit number, it is going to be the 16 combinations are there, because it is going to be 2 power 4. It is going to be the 2 power 4. Wait a minute. It is going to be the 2 power 4. 2 power 4 means total 16 combinations are there. And they are named as, I am just taking them as a hexadecimal number varying from 0 to F. Hexadecimal number varying from 0 to F. Let me tell you one important point. In the hexadecimal case, uh, we are having the starting number is a 0 and ending number is a f. Starting number is a 0 and ending number is a f. So let me explain 2 more minutes of information for this, because this one I'm going to take this example in the stack explanation. So here f is there na. If you subtract 1 from the f, it is going to be the previous digit, that is nothing but the e. If you subtract 1 from E, it is going to be the D. If you subtract 1 from D, it is going to be the C. Or I can say that in the decimal format, F is nothing but the 15. In the decimal format. This is the hexadecimal number system, but if you are trying to write the equivalent to decimal value for the hexadecimal number, F is nothing but the 15, E is nothing but the 14, D is nothing but the 13, C is nothing but the 12. Means 15 minus 1 is nothing but the 14. 14 equivalent hexadecimal number is the E. So 14 minus 1 is nothing but the 13. So 13 equivalent hexadecimal number is a D. So means when you are subtracting 1 from the maximum number of the hexadecimal number, you are going to get the previous number. So means the next to that one in the reverse order, in the decrement order. Okay. So F minus 1 means E, E minus 1 means D, D minus 1 means C, C minus 1 means B, A minus 1 means 9, 9 minus 1 means 8, 8 minus 1 means 7, and so on. Okay, why I am taking this explanation, we will come to know that during the explanation of the what we say, the stack operation. Okay, so nibble is nothing but, in brief, nibble is nothing but group of 4 bits is called as a nibble. So let us go for defining the another one, which is nothing but the byte, Group of 8 bits. Byte is nothing but group of 8 bits is called as a byte. So here I took the 16-bit combination in order to indicate that what exactly the 8-bit number. I am going to take this one. So 8-bit number means D0 to if at all I am assuming it as a 8-bit data, then their suffixes are the D0 and the maximum one is the D7. Let me define one more thing also. I think all of you know this one. So the starting bit of a particular bit combination is called as a LSB. Starting bit combination is called as a LSB. Okay. So LSB is nothing but the least significant bit, and the ending combination, the last combination, is called as a MSB. Okay, so it is called as a MSB. Most significant bit. It is called as a most significant bit. Okay, so let me take back here. Okay, not required. I think all of you know that one, but let me write. MSB is nothing but the most significant bit. MSB is nothing but the most significant bit. In the previous slide is also LSB is nothing but D0. D3 is called as a MSB, most significant bit. Okay. So here we are having the 8-bit number. They are varying from D0 to D7. I can call that 8-bit number is what is that? Byte is nothing but group of 8-bit number. Group of 8-bit number is called as a byte. group of 8-bit number is called as a byte. And we may have, see, group of 8-bit means they are varying from where? From the D7 to the D0. They are varying from D7 to the D0. Okay. So if at all, this particular 8-bit number can be rewritten in terms of, or can be called in terms of the nibble format. Can be called in terms of the nibble format. Okay. So what I am going to do is this part. Sorry. So this part is called as a nibble. Group of 4 bits we define a, it is a nibble, and another nibble is going to be this part. Group of 2 nibbles is called as a byte, or group of 8 bits is called as a nibble. Sorry, group of 8 bits is called as a byte. Two definitions. Group of 2 nibbles arranged in the sequential order is called as a byte, or group of 8 bits. In simple format, you don't write the definition in terms of the nibble format. Simply write that group of 8 bits is nothing but the byte. Group of 8 bits is not 8 bits is nothing but the byte. Okay. So this one is called as a lower nibble. So it is in the nibble format now. This one. So when you are assigning the names, you are supposed to move from the least significant bit to the most significant bit, right to left. So this one is called as a lower nibble. This one is called as a higher nibble. This one is called as a lower nibble. This one is called as a higher nibble. Okay, now this is all about the byte explanation. This is all about the byte explanation. Now let us go for the word. Okay, now. So word is nothing but group of 16 bits. Word is nothing but group of 16 bits. They are varying from D0 to D7. They are varying from D0 to D7. And this word is a group of, this word is a group of 2 bytes. So here we are having a 16-bit number now. Word is nothing but group of 16 bits is called as a word, and this particular 16-bit is divided into two 8-bit format. Okay, two 8-bit format. So this part is called as a lower byte. This part is called as a lower byte, and this part is called as a higher byte. So this part is called as a higher byte. Okay, so one is a lower byte combination, another one is a higher byte. Means group of 16 bits is called as a word, group of 16 bits is called as a word, and this word can be rewritten in terms of the byte format. So first 8 bits, when you are moving from the right to left combination, when you are moving from the right to left combination, then first 8 bits are called as a lower byte, and next 8 bits are called as a higher byte. First 8 bits are called as a lower byte, and next 8 bits are called as a higher byte. Okay. So because of that, during the explanation of the architecture of 8086 microprocessor, we have seen one naming convention. I'm going to take the accumulator concept. So here the 8 bits is called as a AH na. AH is nothing but the accumulator higher byte. AH is nothing but the accumulator higher byte, and this group I'm going to call it as a lower byte. Okay, now. So it is nothing but the A. It is going to be the accumulator lower byte. One is the accumulator higher byte, which is nothing but the in 16-bit combination. It is going to be the D8 to D15 is called as a higher byte, and D0 to D7 are called as a lower byte. D7 to D0 are called D0 to D7 are called as a lower byte. So it is the byte concept. Means group of 2 bytes. Group of 2 bytes is called as a word, or in simple format, the group of 16-bit number is called as a word. Next one is a double. So because of the space restriction, I am not taking this particular cell combination to explain the word double. Double is nothing but the 32-bit number. Group of 32-bit number is called as a double. Group of 32-bit number is called as a what is that? Group of 32-bit number is called as a double. So let me write that one. So I'm just typing that. So that the double is nothing but a group of 32 bits now. Then the most significant bit is going to be the 31, and the least significant bit is, most significant bit is going to be the 31, and the least one is going to be the 0. Least one is going to be the 0. And one more thing is 0 to 15. I'm just typing this. 0 to 15 is called as a lower word, and 16 to 16 to 16 to sorry 16 to 31. So 0 to 15 is called as a 0 to 15 is called as a lower word. 16 to 31 is called as a higher word, because double is nothing but group of two words is called as a group of two words is called as a double. Double is nothing but group of 32 bit number. Group of 32 bit number. The bit number combinations are varying from 0 to 31. Big group bit combination is varying from 0 to 31. This is all about the double. This is all about the double. Okay, now. So let us go for the stack explanation. I think all of us are aware of this one, right? So I hope all of you cleared the doubts. Means what exactly the bit, what exactly the nibble, what exactly the byte, word, and the double. So what we do is let us review. So this one is going to be the bit is nothing but one bit combination is called as a bit. That may be the 0 or 1. Nibble is nothing but group of 8 bits is called as a nibble. Byte is nothing but group of 8 bits is called as a byte. And group of 8 bits is called as a byte. And it is a combination of the two nibbles. Means 4 bit is grouped as a one nibble. So lower nibble and the higher nibble. And next one is the word. Word is nothing but group of 16 bits is called as a word. And the first 8 bits is called as a lower byte. And the second 8 bit is called as a higher byte, because the word is nothing but group of two bytes. Group of two bytes. One byte is called as a lower byte, another byte is called as a higher byte. And the double is nothing but group of 32 bit number is called as a double. Okay. So this is all about the what exactly the bit, nibble, all those things. Now, whatever the bit combinations we are having over here, whatever the bit combinations we are having over here. So let us suppose I'm taking the word combination. I'm taking the word combination. So word is nothing but what? It is a 16 bit number now. Word is nothing but word is nothing but it is a 16-bit number, na? It is a 16-bit number. Okay. Uh, because I need to explain this one. This is the last point. So group of 16-bit number, na? Okay. So this is the I'm splitting this entire bit combination. That may be the 8-bit or 16-bit or the 32-bit. This one is exactly split into 4-bit 4-bit format. Exactly split it into 4-bit format, which is nothing but we call it as a nibble format. We call it as a nibble format. Okay, now we call it as a nibble format. Okay, nibble format. Actually, this number is what ma 16-bit number, varying from D0 to D50. But I'm splitting that one into the what is that the 4-bit format, because I told you that even though microprocessor is performing its operations using the binary number system, the information is going to be stored in terms of the hexadecimal number system. The information is going to be stored in terms of the hexadecimal number system. So how exactly the equivalent hexadecimal number is going to be written means that is going to be done using the 4-bit combination. Means if you are having the 16-bit number, what you do is you move from the right to left concept. Again, same thing what we have seen. You move from right to left concept. You move from right to left concept. So right to left means move from right to left and split that one into the 4-bit combination. And each 4-bit is going to represent the each 4-bit is going to represent one nibble. And in the 4-bit format only we are having the hexadecimal equivalent value. Hexadecimal equivalent value. For example, I'm having the 0009. Okay now. So why I'm taking this, you will come to know that point. I'll do is I'll take 0009H. See ma 0009H is what ma? 0009H is actually 0009H is a 4-digit hexadecimal number. 0009H is a 4-digit hexadecimal number. Okay na? Hexadecimal number. 4-digit hexadecimal number na. So in order to represent each digit in the hexadecimal combination, how many bits we require, or otherwise in order to represent one hexadecimal number, that may be varying from 0 to F, 0, 1, 2, 3, and so on to the F. How many bits we require? 4 bits we require. How many bits we require? I'm sorry. How many bits we require? 4 bits we require. I don't know whether I didn't. Yeah, I done the transition. I thought that I'm not done the transition. So I'm not done that one, then definitely. Yeah. So here we are having the uh, splitting, means when you are having the 16-bit number, if you The microprocessor is working based on the binary number system. Microprocessor is working based on the binary number system, but the information is going to be stored inside the memory in terms of the hexadecimal number system. So that's why, as I done, it is going to be the group of 4 bits. It's going to be the group of 4 bits. Sorry, group of 4 bits. Group of 4 bits. Okay, na? So it is a group of 4 bits. Each 4-bit combination is nothing but the hexadecimal equivalent. Each 4-bit combination is nothing but the hexadecimal equivalent. Let us suppose I'm having one number called as a, I'll take the same number what I took, 0009H. 0009H. 0009H is nothing but what, ma? It is going to be the 4-digit. It is not the bit. It is a 4-digit hexadecimal number. It is a 4-digit hexadecimal number. The first digit of the hexadecimal number is a 0. I can call this one as the most significant digit. Most significant digit of the what 4-digit hexadecimal number. So this is the hexadecimal number 0. This is the hexadecimal number 0. This is the hexadecimal number 0. This is the hexadecimal number 9. Otherwise, I'll take another one because all are zeros now. So I'll take one more thing. I'll take 1009H. 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 In this case, 1 is the most significant digit of the hexadecimal number. 0 is the another digit, hexadecimal digit. 0 is the another hexadecimal digit. 9 is the another hexadecimal digit. How many hexadecimal digits are there? 4. How many hexadecimal digits are there? 4, right? So they are the 4 digits. They are the 4 digits, and each digit require how many combinations? 4-bit combination. Means if you want to represent 9, how many combinations we are taking? Just recollect the 4-bit combination what we took from the minimum to maximum, 4 zeros to 4 ones. So in order to represent the 9, how many bits we require? 4 bits. In order to represent the 0, how many bits we require? 0. 4 bits. In order to represent the 0, how many bits we require? 4 bits. In order to represent the 1, how many bits we require? 4 bits. Okay. So means 4 digits are there. Each digit requires the 4 bits to represent because each digit is a hexadecimal digit. If you want to represent that one in the binary combination, for each digit we require the 4-bit number. So total how many bits are there? 4 into 4, which is nothing but the 16. Let me rewrite this one. So in order to represent 1, how many digits we require, ma? In order to represent the hexadecimal number 1, how many binary bits we require? 4. So I'm just writing that particular binary bit combination. And putting. I'm just writing triple 0 1. Triple 0 1. Okay. Now I'm going to take the color change. For 1, how many bits we require? 4 bits. This is what the first nibble. Okay. Now for 0, how many bits we require? Again the 4. Again the 4. Okay. So it is going to be the 0 0 0 0. Okay. Next case the next is the another 0. Another 0 means one more 0 combination. We are going to get one more 0 combination. 0 0 0 0. For 9, how many bits we require? For 9, I'm going to take the red mark. Yeah. For 9, how many bits we require? Again 4 bits. Again 4 bits. Okay. So it is going to be the, in order to represent the 9 in terms of the binary combination, it is going to be 1 double 0 1 1 double 0 1. Now look at this one. So to write the 4-digit hexadecimal number, how many bits would require? 16. How many bits would require? 16. Why I am showing all these things means when you are going to assign the addresses, you are supposed to do the splitting operation. You are supposed to take the address combinations from minimum to maximum. You should move from the right to left and split each 4-bit as a one group. Each 4-bit as a one group. So if you are doing like that, then 1009, which is the hexadecimal number, its equivalent binary combination is going to be the 0001 4 zeros, 4 zeros, 1001. This is the equivalent binary bit combination. Equivalent binary bit combination. Okay. So how this is what exactly how the binary bit is going to be converted into the hexadecimal number by taking the group of 4 bits, 4 bits, 4 bits. By moving from right to left, it is converted. Binary bit combination is converted into the what is it, hexadecimal number. Hexadecimal number. Okay. So this is all about our brief explanation of our bit, nibble, byte, and all those things. Okay. Okay. So the next case is the stack operation. So what I'll do is I'll split this video. I'll stop the video right over here. I'll go for the stack operation. I'll prepare the stack also, and I'll try to upload both videos. So whichever the video is going to be uploaded first, that I'm going to send you. Okay. So no problem. So I'm going to alter this explanation right now because it is taking more data when I'm going to upload. So it's very difficult for me to what is